Good morning, dear students. Today I will have a session on an expression for magnetic force on a current carrying conductor. Do remember I have a small expression for magnetic force acting on a charge. If a charge particle is moving, an expression for magnetic force is F equal to Q V cross B. Now today's session will have magnetic force due to current carrying conductor. The title is very simple. Finally, we'll have an expression for force that is nothing but magnetic force. You have a conductor, the conductor is supporting current in it. When a conductor means charges are moving inside a wire, electrons are moving inside. When a wire is supporting current in it, what is the magnetic force on it due to a current in a wire? Now think you have a small wire of certain length. Yes. Now think this is your wire. Let me put it some extra wire. Think the current in this wire is I. Now this wire is subjected to an external magnetic field B. Let B be the field. It is called external field. Let B be the magnetic field. There is a region where B is a magnetic field. Now you have wire which is carrying some current I. It is carrying current I. This is your wire. And I need to have an expression for magnetic force due to a current carrying conductor. Let me start. We know that magnetic force on a charged particle is magnetic force on a charged particle, on a moving charged particle, on a moving charge particle, on a moving charge particle is Fm equal to Q V cross B, and this is nothing but Q VB sine of theta or n vector. This is our mathematics over. Now I'm interested in what is the magnetic force due to current carrying conductor. Let the length of the wire, let L be the length of wire and I be current. Let I be the current. Yes. Now the magnetic force, see when I say a wire, current is there. This current is due to electrons and movement of charge carriers in a wire. In case of a conductor, the free charge carriers means the charges which move, which gives rise to current, they are made up of electrons. Not one electron is moving, a huge number of electrons are moving. Let n be the number of electrons. Let n, it is called, let n be the number density. Let n be the number density of charge carriers. Number density of charge carriers. When I say n, number density means equal to number divided by volume. Do remember this. Small n stands for number of charge carriers in a given time interval. If these are the cases, if for one charge, what is the magnetic force? Fm equal to magnetic. If there is one charge, this is called, you have one charge which is moving with velocity v, and the magnetic force is given by qv into b. If there are n number of charge carriers, n I have written here, n means number density. If there are n charges and each with a charge e, electronic charge e, now, and all are moving with a velocity v. Let me write this formula once again. F equivalent to NQ is total, N is number of charge carriers per unit volume, and this N is takes care of this. Look at it, this formula V is there hidden, it is number into charge. Now what I need to do, this formula, it should be multiplied in area into length, and this is whole is a charge into velocity vector into cross B. So what is this? This whole is I. Because you have n number of charges, means n means number of charges per volume. So this is just a pure number, this n into q. But what is the volume? This get nullified mathematically because charge, this n here is one charge. So n becomes a number provided this n is made up of number divided by volume. Volume means area into length. So hence this n can be written as like this, n upon A into L. To nullify the dimensional analysis, I need to write small n q a l. Together this is taken as total charge. It is called total charge. Total charge which is moving with velocity v and it is going to cross. Now the simplification gives me n q a l v. This q is an electronic charge. Let me write it here. N a l. Then you have a QE. Q means electronic charge into velocity into a cross product. I have replaced with this formula. Now we know that when electrons move, it gives rise to current. I need to replace this whole with in terms of a current. What is the next concept? Now look at it, take it as A on the other side. Let it be. This N QE into L, then you have a. This is A. Into, you write it formula, one more formula here. Yes. This V, then A, of course, L cross B. See, all the things I have taken it outside. Now look at it. V is a velocity, QE is a charge, N is a number density, this area. This whole, look at this mathematical equation. This is totally going to be your current density. What is meant by current density? Let me write the formula. Current density J equal to current divided by area. So what is this current? Current is default written as all these relations. I equal to number of charge carriers, N into electronic charge into AL. It is just V. So this is going to be current. Remember current electricity chapter, we have current is defined as NEAVD. It is V happens to be drift velocity. So in this relationship, NQV and A is going to be the total current. This is called current. So what I mean to say, you want a current density. So this area comes here, it becomes a current density, NEA. So finally, what I mean to say, I'm going to write my mathematical force in terms of which becomes F equal to I. This is I, up to here is I L cross B. Now current cannot be a vector. This length is taken as a vector. Length is also not a vector, but to make mathematics very simple, since velocity is included into the formula, NEAVD, like this current is defined as NEAVD, V is a velocity of all the charged particle, hence I can write magnetic force is written as in terms of current length I L cross B. Look at this relation. It is for a single charge, it is Q V cross B. For the whole wire, it is F equal to I L cross B. Yes, the final expression is, we noticed that current is equivalent to QNEAVD. So what is current? In terms of this force equal to, in terms of current density, magnetic force is equal to J, A, of course, your L cross B. Instead of writing L cross B, I will write L is a scalar quantity, L cross B. This whole is a product. This whole is actually your QV. It is an individual charge into velocity. Here the total current is nothing but in terms of current. Actually it is J cross B. Or I can put it A and L remain silent. In terms of current it becomes I L cross B. Do remember in most of the mathematical calculation, you'll be using this formula IL cross B, or in terms of current density, it is JAL, because JA together becomes current. Because I already defined J equal to your I equal to current equal to J into A. Current is equal to, yes, J into A is nothing but current. Current L as vector. This is going to be your key relationship for magnetic force. The second part of the topic is motion in combined electric and magnetic fields. When a charged particle is subjected to electric and magnetic field, when a charged particle is subjected to electric as well as magnetic field, where electric field and magnetic field are 90-degree apart, means the direction of electric field, if you take it as x-axis, magnetic field is along y-axis, and what will be the influence of this moving charge? Means a charged carrier which is moving with some velocity, it enters into a region where electric field is present, magnetic field is present. Then how this charge experiences the force? Means it is acted by electric force, it is acted by magnetic force. When both are acting, what will be its resultant direction of motion? That is called motion of a charged particle, charge carrying particle in a combined electric and magnetic field. Let me have a small diagram which will tell you. Finally, we will learn how a charged particle moving with a specific velocity is selected from a different charged particle. It means, take for example, particles when they come out from accelerators. Accelerator means a device where charged particles move with different velocity. A loose example. If students are present in a classroom, different students have different academic skills. How to pick a particular academic student, whether he is good in this or that. So it is called velocity selector. I want to select a particular velocity of a charged particle. To select, this method is adopted. The method is called motion of a charged particles. They are moving at different velocities. I want to select a particular velocity. This concept finds an application. Let me have a small diagram. Yes, this is an axis. This is one axis, the other axis, the third axis. All are mutually perpendicular. Yes, the things are very clear. Let me take it as x-axis. Here I will start. Let me take it as y-axis. Let me take it as z-axis. And I hope all are familiar. X-axis means I vector, y-axis means j vector, and z-axis means k vector. This is your origin. Now consider your electric field is along y-axis, or it is j vector. Magnetic field is along, yes, magnetic field is along k vector. Electric field is along y-axis, magnetic field is along z-axis. The angle between electric field and magnetic field are mutually perpendicular. Now consider a particle which is moving along x-axis. It is moving along x-axis. Q into V, which is moving along I vector. The particle is moving along x-axis, means a particle with velocity V, there are a large number of particles which enter with velocity V, making an angle 90 degree. The particle enters, and think the particle is moving with direction x-axis. Now, net force acting on the particle, there are two forces which is equivalent to sum of electric force plus magnetic force. Now the condition is, when two forces are acting on a particle, what are the associated, the respective forces? The charged particle experiences an electric force, the charged particle experiences a magnetic force. Think the magnitude of electric force, I repeat, the magnitude of electric force, the magnitude of magnetic force, both are equal in magnitude and opposite in direction. Then what happens? The net force becomes, this net force becomes zero. When the net force on the charged particle becomes zero, that particle moves undeflected. If the net force acting on this charged particle is zero, that particle moves undeflected. What is undeflected? If it is moving in x direction, it continues to move in x direction. Means think electric field is along y-axis, magnetic field is along z-axis, particle is moving along x-axis. Let me start the mathematical equation taking into this account. The two forces are electric force is equal to magnetic force. Now when this happens, look at this relation. If charge is moving along this direction, this is I direction, and electric field is here, what is the direction of electric force? Electric force will be same direction. It is Fe. Why? Think the charge is positive. The direction of the force is along the direction of electric field. If electric field is along y-axis, the electric force is also along y-axis. But this force, magnetic force, is given by, there is no issue. This is just QE and it is a J vector. Whereas magnetic force, as we all know, magnetic force is equal to Q V I cross, because the direction of a charged particle, into magnetic field. Magnetic field is along K vector direction. Now the relation becomes Q V B I cross K. It is like X cross Z. X cross Z is minus Y. Minus Y is written as minus J vector. I hope it's very simple. Now my magnetic force is minus Q V B into J vector. This minus is taken care here. Now this is going to be Z direction, Y direction. From here, X positive, I positive, Y positive, J positive, both are one and same. Here, now this is taken as a diagram. This is going to be negative direction. This is minus Z, sorry, minus J, sorry, minus Y, and this is going to be minus J vector. Now the direction of magnetic force is here. Magnetic force is along minus J direction. Do remember, when a charged particle is moving along x-axis, electric field along y-axis, magnetic field along z-axis. Yes, z-axis. What is the direction of electric force? Electric field is y, electric force is also y. Magnetic field is z-axis or a k vector. Magnetic force, magnetic field is k, magnetic force is minus j. That's why I written minus of q v b j. Both will celebrate. Left with this relation j vector cancels. Left with electric field, check it out, equal to vb. This minus symbolizes just the direction. So finally, what is the relationship? The relationship is vb. So this gives you relationship velocity equivalent to electric field divided by b. What is this relationship? What is this? When the particle is moving under the influence of combined electric and magnetic field, electric force is along plus j direction, magnetic force is along minus j direction. If the magnitude of electric force is equal to magnitude of magnetic force, if they are equal in magnitude and opposite in direction, the net force is going to be zero. If the net force acting on the particle is zero, the particle moves undeflected. It continues to move in a direction of x-axis. So when it continues to move in a direction of x-axis, the net force is zero. This is the mathematical relation. We will get a velocity formula. Velocity of that charged particle is going to be electric field magnitude divided by magnetic field value, means the ratio of electric field to magnetic field. This is called velocity selector method.